is that observations during the first days or weeks after explosion are really key for getting unique information about supernova progenitors. Some of the things I'll talk about is how we can actually constrain the radius of the exploding star, look for interaction with a companion, and probe the circumstellar material that's reflecting the activity of the progenitor right before death, which has been an interesting theme in recent years, that massive stars might have a lot of activity before they die. And I just want to mention, there's also this fantastic recent review of shock theory by Eli Waxman and Boris Katz, part of the Supernovae handbook that's on the archive now that I really recommend reading, that covers a lot of the physics behind this. And so what do we see when we first see a star explode? So what you have, right, is a shock propagating through the star from the inside out toward the surface. And at any given time, the time it takes a shock to cover, let's say, some distance delta r is just going to be that distance divided by the speed of the shock, right? And at the same time, there's going to be the photons that are powering that shock forward. And the time it takes those photons to diffuse across that same distance is just going to be the light travel time across that distance times the optical depth. And so what's going to happen is you're getting close, the shock is getting closer and closer to the surface of the star. This diffusion time is getting shorter and shorter until it's shorter than the shock crossing time, and those photons are now going to leak out, and it's not going to power your shock anymore. And so you can just equate these two time scales and see that below an optical depth of roughly the speed of the light divided by the speed of your shock, which is roughly 30 for a kind of a typical supernova, you're going to have your shock breakout. And that's going to give rise to your shock breakout flash. I just want to make that distinction because in the literature often this is confused with the shock cooling phase, which then comes subsequently. Okay, so following the shock breakout, this is our first sign that a star has exploded. We see the shock cooling. So you have all this hot, shock-heated material that's now going to expand out and provide emission as it cools. And we first worked this out in the case of type 1a supernova a few years ago now, when I was a postdoc at UC Berkeley with Phil Chang and Evan Weinberg. And it's just a light curve over time for a couple different radii for your exploding star. And what we found that was exciting about this is that this luminosity that you see from the shock cooling phase roughly scales proportional to your progenitor radius. So this is roughly how the luminosity scales. You can see the progenitor radius. The speed of light, we know what that is. This is the opacity that depends just on the composition. And then the energy per unit mass of the explosion, which doesn't change too much. It's roughly like an MeV per nucleon. So the thing that can really change by orders of magnitude as an equation is the radius. And so that's what you're really able to constrain measuring the shock cooling. And so this gives you a direct connection to the progenitor star that exploded. Now you might wonder, why was I working this out for white dwarfs and type 1a supernova, knowing that I figured out it roughly scales with the radius? Why would I do this for like an Earth radius star? I wasn't thinking very forward at this time, I guess, just out of grad school. But of course, Ahud Nakar and Ansari thought ahead and said, well, maybe this should be done for stars with larger radii. And indeed, they had this nice paper working out for red supergiants, blue supergiants, and Wolf-Rayet stars, all with the shock cooling signatures you should have. And indeed, they found that it roughly scales with the radius of the star. And this has kind of become the standard that people have now been adding details in forthcoming years for shock cooling. So why does it scale with the radius of the star? So there's kind of a toy picture I like to present that shows how this works. So you imagine a star, because if you think about it, right, the star's been expanding for many days. It's much larger than the initial radius. So why should it reflect the initial radius it had when it was much, much smaller? And the basic idea is, right, you shock heat a star and it starts expanding. And just like if you take purse your lips and you blow air out of your mouth, you can feel the air cool. You can feel the air cools, right, as it spreads out, as it expands. And indeed, that's what a star does as well. As it expands, the energy density goes down. But now if you take a larger radius star to begin with, it's going to again expand and cool, but once you get to the same radius, the fractional change in radius you've had is going to be less, right? And so you're not going to cool as much, okay? And so it's going to end up being a brighter signature. And so that's why you get something that's roughly proportional to the radius of the star. So hopefully it's easy to remember now. Okay, so even though we did this initially in the case of 1As, which probably wasn't the best idea, we ended up actually getting extremely lucky. And within a year after this theory was developed, we had one of the closest supernova in many decades, 2011 FE. And so this was a case where we actually had, this is the rising light curve in G-band, days such as explosion. This is work by Josh Bloom. And so you can see PTF had data points at roughly 11 hours after explosion, about a day and a half. And there was also this upper limit here that you had to satisfy. And so what you expect is a light curve that's going to kind of drop from shock cooling and then rise once nickel 56 is turning on and powering your supernova. And so this was compared to numbers of our own work. Rubinick and Waxman did a more detailed treatment of this. And then Dan Cason's work, which I'll get back to in a little while. What we expect is for a given radius star, you're going to have some shock cooling signature and then rise up. And since this is, you have to be below this upper limit, this really constrains the radius of your exploding star to be small, less than a 50th of a solar radius. And so even though people have suspected this and felt like we've known it for many decades, this is really some of the first direct evidence that type 1a supernova have to be coming from a very compact star. Okay? But in most cases, we're not always able to get onto supernova, the 1As early enough to be able to do this sort of measurement. And so a lot of cases, what we're doing instead is constraining for interactions. And so this is work that Dan Cason's really well known for, of looking at if you had a single degenerate sort of scenario, and you have your white dwarf explosion interacting with the non-degenerate companion, you're going to see, if you're looking down this funnel here, all this shock-heated material, and potentially it's going to give you additional emission during the rise. And so this was work with Ben Shappy for Assassin 14LP. And so here's the data as the supernova is rising in an upper limit. And in this case, you can't really constrain the radius of the star itself, the progenitor that's exploding, but you can potentially constrain the companion, at least for certain viewing angles. And that's what we did in this case. You can see, depending on the explosion time, which is a little uncertain, you can constrain different radii for the stars if it was interacting with a non-degenerate companion. Okay. And we're not the only one that's doing this. This has kind of become a game whenever you find an early supernova to try to constrain these sort of light curves. Okay, so this is another example of this really nice work by Rob Oling and many collaborators that are here. There was 3 exquisite light curves by Kepler. I'm just showing 2 of them right here, but you can see you just have this amazing coverage. And in all 3 cases, there was no evidence for a companion. Okay, but that's not how it always is. Sometimes there actually is some evidence for a potential companion. And this is usually seen by some sort of excess in blue light at early times. So this is work by Yi Kao on a kind of type 1a supernova, but not really a normal one. It's one of this kind of subluminous subclass of type 1as. But you can see at Swift, compared to most normal type 1as, there's this additional emission for this first data point or so. And then for a more normal type 1a, this is 12CG if you're a 1a aficionado. This is work by Howie Marion, and again, Jeff Soderman and other people here. Again, you can see for Swift, there's this additional emission at early times that potentially support for a single degenerate scenario. And also see there's been also work on 2015F. There's the poster in this conference on this event as well. Okay. So in the case of the core collapse, we can go back and do the actual shock cooling of the exploding star itself, not so much the companion. And again, you can get potential upper limits, work by data by Alessandro Corsi, again, Yi Kao, finding for these stripped envelope supernovae. So this is a 1C, this is a 1B. Thanks again, because you have all these upper limits. You have some data points of the rising supernova, and you try to fit what's the largest star, progenitor star exploding, that you could fit under these limits. In each case, you're finding that they're rather compact, pretty consistent with what we expect for a strip star. So this is kind of boring. I'm showing you guys a lot of upper limits, but in fact, there are cases where we see the shock cooling directly, and we get really nice measurements of the progenitor. And this is best shown and for these type 2b supernovae. And so these ones are kind of unique and that they seem to have this very extended tenuous envelope, low mass, but order many hundreds of solar radii. And this leads to a really distinct shock pulling signature. Because it's low mass, you end up getting rapid cooling after you get to the peak luminosity. And this is worked out by Stan Lucy and others initially. And so interestingly, a lot of these have been shown with pre-explosion imaging to also have pretty unique progenitors, because we can see that many of them are yellow supergiants. And so now you can really play this game, best kind of shown by the nice work by Melina Burston, where you can explode a series of different progenitors. You can see this is for 11DH, and here's a G-band light curve coming down, and this is a log space, so this is the main nickel peak. But you can consider different radii for this extended material and really constrain it well with this sort of modeling. Okay. So where are we going forward from this now? So I've been in collaboration with Victoria Morozova. This is work she's mainly been leading. She was a postdoc at Caltech, and now she's moving on to Princeton in the fall as a postdoc. An open source code for doing supernova explosions and producing light curves. So this is the supernova explosion code, or SNEP. It's basically a simple thing where you can take your favorite stellar model from Kepler, Mesa, or whatever, explode it and produce some quick light curves and do some nice comparisons with observations and various bolometric light curves or different wave bands. And I just want to point out it's open source, so you can go to this website and download it yourself. We're really excited if you can try it out and give us feedback, because we'd like to have more iterations where we can improve the code. It's already being used by a number of people, both for papers and also as a teaching tool. There's a poster by Francesco Teddia using some stuff from SNEC here. And a big thank you to Melina Burston. This is very similar to the code she's been using for her own work, and she's been really helpful and giving us test models and answering our questions when we've had numerical troubles and helping us being able to develop the code. So what we've been doing with this, now we can do lots of fun and numerical experiments. So for example, this summer I've had a undergrad from Caltech, Mark Wilson, actually looking at different types of circumstellar material around a stripped envelope supernova to see what kind of impact you get on the light curve. And so this is a comparison of V-band absolute magnitude versus time. You can see here the density profile as the photosphere is passing back through this this envelope profile into the main compact star. And we can consider different things like what's the difference between a wind profile or a convective profile and so forth. Another thing we've been considering is type 1a supernovae, whether you can see any signs of circumstellar material if they had additional material around them from the progenitor scenario. Because if you think about it, a lot of type 1a scenarios, you have things, mass transfer, that's not going to be completely efficient. So you might have some nova material, some material left over from a merger. And so here's just some examples to get an idea of, there's density versus radius. This is kind of a normal bare white dwarf. But you might expect, for example, from a merger that you might have some more extended material there. So the question is, can we constrain this with the light curves the data that we're taking? And one of the best ways we found to actually constrain this is potentially from the early color evolution. Because what happens is, as the shock passes through the material, this extended material, it gets very hot. And so this is B minus V magnitude as a function of time after the explosion for different radii of kind of extended circumstellar material around a type 1a. And you can see it becomes much bluer at earlier times, whereas a normal 1a might be more like this. And here's just it's not any proof, but this is just a comparison. But this is 2012 CG. This is this event that maybe has a companion. And you can see here, this is again B minus V, and right here, the stars are kind of a more normal supernova. The diamonds is 11 Fe, kind of like how a normal 1A would evolve. And you can see 12 CG is also kind of blue at early times. So this might be a companion. It could also maybe be evidence of circumstellar material in this case. And so these maybe look like exotic scenarios of, you take a 1A, you put circumstellar stuff around it. Do we really believe that? But what's interesting is I think there's also building a lot of evidence that even in more vanilla supernova that there's stuff around them. And so this is a study by Nagy and Dinko, which I think is it didn't come out too long ago, but I think it's somewhat underappreciated, where they took type 2Ps, And the normal type 2 would be, it's hard to see here a little bit, but it's kind of bright green right here. And these are just using kind of semi-analytic models that they developed. And they added in some additional shock heating, shock cooling at early times. And they're finding that they're getting much better fits to these light curves. And if you think about what is this really implying about this, it seems to be extended material with maybe a few thousand solar radii or so, and a mass of around a tenth of a solar mass of additional material out there. And motivated by this, we've been doing more detailed comparisons with SNAP. This is work that Victoria is leading again, where we take this kind of normal 2Ps, and this is great data from Stefano and LCOGT that are just building up this great data set to compare to. And you can see that our best fit model with MESA is these blue curves here, after doing a huge grid of different models. And then if we just add a little bit of circumstellar material, you can see, especially at early times, we do much better at getting these light curves. Very consistent with what was being found before, but now we're comparing with all different wave bands, and we're still finding that this is working out really well. And so this has really interesting implications about how massive stars are evolving and changing the last few months of their lives. So it's going to be interesting to see how this develops and see how, as we do a larger population of these, how much variety there is in this. Going forward, I think it's going to be a really great time for doing more of these types of studies, and so I think this is just going to get more and more popular. You've already heard about a lot of different transient surveys that are going on, such as Assassin, IPTF, and ZTF in the future. And so, since you've heard about those, I just want to kind of emphasize one particular study I'm especially interested in. And that is doing a wide field transient survey, but in the ultraviolet. And so this is CUTI, the CubeSat Ultraviolet Transient Imaging Experiment. And so we already have a pretty good acronym, so I think we're already halfway there to having a successful project. And so I was a co-PI of this. This is a proposal we put into NASA in the spring. And this is led by the PI, Brad Sanko from Goddard. And so this is a CubeSat mission to basically do very wide field imaging. So you can see this is a 120 square degree field of view of CUTI versus Galax, the full moon, and the SWIFT, the UVOT. So you can see this is just a huge field of view. And the idea is just to take 3-minute snapshots down to 19th magnitude and take 14 of these every orbit. So you're getting every orbit you're getting 1,700 square degrees. Okay, and this is going to be great for stellar flares, AGN variability, blah, 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 but for core collapse shock cooling, this is really going to revolutionize things. And so here's just some examples of what these light curves look like. A light curve with 90-minute cadence, you can see down to 19.2 magnitudes. And so this would be a kind of a vanilla red supergiant at 100 megaparsecs, and you just get this exquisite light curve here. And then we can even stack for even deeper observations and still get really great coverage of the shock cooling phase here. You can see. So the shock breakout, of course, is just right here. We're not able to resolve that at all, but the shock cooling, we can really measure that in detail. And the monthly discovery rates sound really promising. So just with this sort of mode of operation, you're going to have something like 10 red supergiants a month, and maybe even more if you do stacking. 2 yellow supergiants, kind of these double peak things that I was talking about before. And maybe a hydrogen strip supernova once a month or so. And so, and in addition, this is going to be a great probe of the circumstellar material and the previous mass loss that these stars have had. So I'm really excited about having some sort of project like this in the future. So I guess I went much faster than I was expecting, but so just to conclude, I hope you take away that early light curves are really providing new and valuable information about exploding stars. I gave some examples where you can do shock cooling non-detections, and they still provide interesting radius constraints for type 1a supernova progenitors and strict envelope supernovae. And in other cases, we're already starting to get direct measurements of the radius of extended material. For example, this very unique type 2b's, where you have this kind of double peak light curve. And even many type 2Ps, we're starting to find that there's evidence of extended maybe wind material around these that's affecting the early light curves. This has been used as evidence or not for non-degenerate companions, for type 1As, for looking with the shock interaction with the companion. And I think this is really going to be something that's just going to continue to grow and explode in coming years as current and future wide field surveys give us even more data. And I think on top of this, UV surveys especially would really revolutionize our understanding of supernova progenitors. So I hope this is something the community keeps thinking about and pushing toward, because it really changed things. So thank you.
Okay, comments, questions?
You had mentioned the extended material around the yellow supergiants that you were able to observe, and you mentioned something similar for the red supergiants. I was wondering if you've been able to kind of backtrack and take the implied mass loss rate from that and see if it agrees with mass loss rates that have been observationally measured for these types of stars. You wouldn't necessarily expect them to perfectly agree, but it would be cool to see if they were in the same ballpark.
So you can tell me it's about a tenth of the solar mass over 3 months.
Okay, I'll translate that into years. Cool.
It's a lot of mass. It's pretty high, right? So
which is good. You want it to be higher than
it's like a hundredth of the solar mass per year.
You'd want it to be higher than the mass loss rates that we measure, because this is presumably the final mass loss before explosion.
I don't have much, how to normalize that. I don't have a good idea. So.
Okay.
So if I remember correctly, snack analysis is proximity diffusion, which becomes less good the earlier you go to the explosion. So are you worried that it might affect some of these inferences in the early parts?
I'm not sure like doing worse what you mean. I mean, what we do not do well yet and we're working on is at early times, you have decoupling of the temperature of like the matter and the photons. And so we might be not getting the quite right temperatures. So that's something that we're working to. But that's kind of the main thing. And that goes away pretty quickly for most of these. At the time scales of like 10 degrees or so that we're really setting these comparisons here.
Yeah, so I don't know if you've seen the work by Joe Anderson. He analyzed these other people as well, the two slopes. So this would be giving us some correlation between the CSM properties and the progenitors, I guess. But have you looked into that?
So what we're doing for this is we have like a lot of data, and we have basically a huge grid of 3 parameters. We have the mass of the star, which we're getting using MESA, the evolved underlying star. And then on top of that, we're putting a wind, which has an extent and a density. So 3 parameters. So the interesting question is, once we do those fits, are there going to be any correlations between those parameters? Like, for example, do the more massive stars tend to have the denser winds, or more extended, or vice versa? So we haven't done enough of these fits yet to know if those correlations are there, but that's something we're really excited about seeing.
So, if there's like a tenth of the solar mass and inflated onto a red supergiant, you calculated what happens to the shock breakout of the equal edge.
So most of these, so there's kind of 2 phases you can get for the shock breakout. You could get a case where the shock breaks out, but there's still a lot of stuff above it, and you can kind of get this diffusion limited shock that's more extended, that people like Chevalier and Avilo and other people have looked at in the past. Most of these are so dense that the shock breakout happens right at the surface of the wind. And so in that case, the shock breakout is kind of just like a shock breakout of a larger radius star. It's not changed too much.
So, I mean, this is a neat question, but for the Cowdell paper, so I was wondering if you can use your code to see if there was shock interaction with the companion, or just with CSM. Is that something you can look at?
So I haven't done a detailed enough comparison. I think just looking at volumetric light curves or even colors, my sense is that's not going to be enough information given some of the stuff I'm finding here. And you're going to want to look at things like velocity profiles and other detailed information. Maybe, for example, look at the late time spectra see if maybe there's some hydrogen there from if there was really a non-degenerate star if it got stripped off. So my main point in showing that is this is a warning that you probably need more information than just seeing one raised Swift point before you claim that there's a companion there.
Thanks.
Okay. Any other question, comments? Okay, thanks again. Okay, good.
So for the same ones where we have this excess luminosity and CSM interaction for the first, it looks like 10 or 20 days. These are not classified as type 2 minutes though.
No, that's right. So all the ones we're considering are 2Ps and 2Ls right now.
So yeah, so we think of hypercapillary symmetry, whatever, the waste is very high. The narrow ones that expect from the CSM interaction.
So yeah, so this is a long-standing question I've had. Even in the case of like the superluminous, the strip supernova that don't show any CSM interaction, is there any possibility that we're missing it somehow and you're not really creating these mirror lines? I don't actually know enough about that line formation. So, but I would really motivate other people to think about that do more detailed radio transfer of, both this and also, like I was just mentioning, like a superluminous type 1 supernova. Can you get interactions that are hidden and you don't see it with narrow line profiles? It's a really bad question.
Okay, thanks again.